Good afternoon, everyone. Welcome to the afternoon session of International Conference. Before proceeding towards the session, I would like to introduce today's resource person, Dr. Mureshwar V. Chaudhary. Sir, Mureshwar V. Chaudhary, sir, is currently working as a postdoctoral research associate at University of Liverpool, England, UK. Sir has completed his master's and bachelor's from University of Pune and PhD from Indian Institute of Science, Education and Research, Pune, India. Sir has also held previous positions as Marie Skłodowska-Curie Postdoctoral Fellow, MSc IF at ICIQ, Tarragona, Spain. Sir has been a postdoctoral research associate from January 2020 to June 2020 in Indian Institute of Science, Education and Research, Pune, India. Sir has 17 research publications in reputed journals. Sir has a book chapter in metal catalyzed synthesis of peroxides. Sir has received various honors and awards like Marie Curie Postdoctoral Individual Fellowship at ICIQ, Spain, Best Poster Award at 8th Conference on Frontiers in Organic Synthesis Technology, Frost 8 by Flow Chemistry Society, Budapest of November 2021, Best Poster Award at 4th UCAM's Conference on Green and Sustainable Chemistry, Tarragona, Spain, Best Poster Award at Alexander von Kashif, India, DST SERB International Travel Grant and Infosys Travel Grant for 4th UCAM's Conference on Green and Sustainable Energy, Tarragona, Spain, in September 2019. CSR Net in 2013 and 14, CSR Senior Research Fellowship in 2019 and IIT GATE 2014. Sir has presented in various conferences and seminars. Sir also has 6 poster presentations. Sir has conducted various outreach activities, workshops, and demonstration. Sir is a scientific reviewer for peer-reviewed journals such as Journal of Flow Chemistry, South African Journal of Chemistry, and Bioorganic Chemistry. With this brief introduction, I welcome Dr. Mureshwar Chaudhary, sir, and I request sir to proceed with the session, and I would also request ma'am to chair the session.
Yes, thank you, madam. Thank you.
Okay, so thank you so much for your kind introduction, and thankful to all organizers for giving me this opportunity to share my work. So am I audible clearly?
Yes, sir.
Okay. So just share the screen. Okay, now, yeah, and my slides are okay, right?
Yes, sir.
Okay, thank you so much. Okay, so the today's talk will be on polymer supported organic catalysis for sustainable asymmetric continuous flow process. This work was carried out at ICIQ, Spain, where I was a Marie Curie postdoctoral fellow. And currently I'm a postdoctoral research associate working at University of Liverpool as an industrial collaborative postdoctor. And here I work on process intensification of some of the monomers, which are going to be useful in polymer industry. So just to give a little photos which I have taken when we visited the Marie Curie Museum in Paris last year, where you can see this is her office, this is her lab, this is her clothes, and then you can see here is the one of the page from her notebook where she calculated the molecular weight for radium. These are the statues available there. So with this now, I will move to the research topic. So my research is basically divided into several topics. Here I just mentioned few, such as flow chemistry, then asymmetric organocatalysis, as well as metal catalysis. So today I will be mostly talking on asymmetric organocatalysis and flow chemistry. And in this talk, you will get to know the aspects of continuous flow chemistry, as well as polymer supported asymmetric catalysis and sustainable process intensification. So if we see the comparison between batch and flow, there are two distinct features, such as in batch, if we see, we take the reactant and add it in the round bottom flask and then stir it to get the final outcome. However, in continuous flow process, there are a continuous flowing of reactants into the reactor streams, and then we can heat or cool down the reactors as we can use a photochemical irradiation also in the reactors, and at the end we collect the product in a continuous manner. So this is nothing but an array of chemical process performed by pumping one or more starting materials in continuous flow streams. So if we see the reactors, the reactor terminology came into the picture in 1945, and they defined it as a reactor, but it was not the first time they used for any reaction, because if you see the thousands of years before also, people were using different type of reactors such as open pot to do some kind of reactions. And then as time passes, the industrial revolution has begun, and the size of the reactors as well as the sophistication of this reactor has changed into the numerously. And now we can see the reactors which are very small and which can be fit into our hand, and they can be used for performing the reaction in a continuous manner. So when I talk about the flow chemistry, basically it will have some major components such as pumps, which will be used to flow the liquid. Then we have the reactor loops, as well as the packed bed reactor. The reactor loops are used to perform the reaction in a homogeneous manner, and packed bed reactors are used to perform the reaction using a heterogeneous catalysis. Then we have a BPR, which is a back pressure regulator, which controls the overall pressure of the reaction. So the beauty of the using the BPR and pressurized system, you can actually heat the solvents about to its boiling point. For example, if you want to use a DCM at 80 degrees Celsius in normal batch reactions, so you cannot go up to that much temperature because boiling point of DCM is around 40 degrees Celsius. However, by using a continuous flow process and placing a BPR to make it a pressurized system, you can use DCM at 80 degrees Celsius also. This is one of the examples just I gave. You can use all type of solvents in a continuous flow manner. And then there will be a downstream unit where inline analytics work of operation can be done in inline. So this is a typical continuous flow setup looks like. This one is the commercial one where you can see the different components, such as, so here there are the tubes to deliver the reactants, and this is the reactor present here, and we can control here a pressure, the flow rate, and the temperature. So in this, the temperature can be controlled by the hot air streams, which are present in these grooves, and we can do the reaction. Here we can see the packed bed reactor where a heterogeneous catalyst can be placed inside the reactor and product can be continuously collected. So there are other options which can be made to make the customized flow reactors, where one can think of using a syringe pump, which will be a more cheaper option. And then the PTFE tubes, these are very cheaply available on internet, or Amazon or Flipkart. And then everyone may have this stirrer as well as the oil bath or water bath as a heating source. So this can be customized to perform the flow reactions. So as I mentioned, there are main 4 types for continuous flow reactions. In the type 1, where there is no catalyst, only 2 reagents are reacted in a temperature control manner to afford a product. Type 2 is a supported reagent, where one reagent will be supported, which will be placed in a back pressure in a packed bed reactor, and then one of the reagent will be passed or will be flown through this reactor to get the product. Type 3 is the homogeneous system where we have to mix our reagents A plus B as well as catalyst in some of container and then just flow it through the reactor to get at the end you will get the product as well as unreacted or recovered catalyst. And then the type 4 is which is a supported catalyst where you make the supported catalyst or you can call it immobilized catalyst or you can call it a heterogeneous catalyst. So these are all similar terminology but not the same. So one can place it in the packed bed reactor and pass the reagents to get a product continuous manner. Why flow chemistry? So when we talk about the green chemistry as well as sustainability, so there are basically 12 principles which must be followed when we perform the reactions. So if we see the principle of green chemistry, and there are few principles which can be followed by a continuous flow chemistry in indirect way. Some of a couple of them I will mention, such as prevent waste, not to clean later, then use of atom economy, as well as design synthesis for energy, and use of real-time analysis, as well as minimize potential for accidents. So by using flow process, we can dramatically reduce the hazards present in the reaction. How it can be done? Because when we are flowing two liquids, there will be in a very small quantity at a certain time, and very small quantity of reagents will come into the contact and they will react, so which will minimize the hazards of the overall reaction. So some more advantages such as the rapid reactions. See in batch reaction, when we add two reagents, then we need to wait for, let's say, to get the complete conversion of the reactants. However, in flow it's not like this. So you just when you react two reactants and they get reacted in a reactor and the product comes out, you can directly start analyzing your reaction mixture. This is due to a greater surface mass to ratio, because at a certain time you will have a very small amount of reactants present at a certain time. And then there will be a byproduct minimization. So how it can be minimized? Since if you see in a typical batch reaction, we add A and B and you get a product C. However, that product C is again get reacted with some of the other present reactant to get a byproduct. But in case of continuous production, it's not like this. Once the product is formed, it will continuously removed from the stream, and which will not allow the byproduct formation. Safety aspect, as I discussed, and the other aspect is the superheating of solvent, which I mentioned in case of DCM, and then real-time analytics. How it can be done by placing kind of instruments such as integration of infrared as well as NMR or UV straight away for one of the stream of the continuous flow product. So there are just a couple of disadvantages, such as you need to solubilize everything into the solution, otherwise it may block the tubing. But nowadays there are advances in the technology, and one can use the slurry also for performing the reaction in continuous manner. And then the commercial instruments, they are a little bit costly. However, if one can think of customization, then it will be available in a cheaper way. So with this now, I will introduce asymmetric organocatalysis. So asymmetric organocatalysis is a method of preparing the chemical compounds by biasing the synthesis in favor of one stereoisomer over another. So why asymmetric synthesis? If you see in nature, most of the compounds present in naturally available sources such as plant as well as animal product as well as marine product, they have an extreme level of enantiomer purity in their compounds. However, so if you see in the chemical biology term, the different enantiomers, they have a different biological activity. For example, if you see this ephedrine, which is a kind of a bronchodilator, where only two isomers are biologically active. However, other two are toxic in nature. So that's why it is very important to synthesize a particular or a specific enantiomer. So in this case, if one can prepare the enantiomer compound, then the dose of the dose of the particular drug also can be lowered, and which can avoid the hazards of unwanted enantiomer. So if you see in the nature, there are plants or marine animals. They make the natural product which have an extreme level of enantiomeric excess, which is more than 99.9999%. However, till today also chemists are trying to mimic the nature and try to get the extreme level of enantiomeric excess. And if someone want to do asymmetric catalysis, this can be done by three ways: by transition metal catalysis, biocatalysis, as well as organocatalysis. So the idea is for an ideal organocatalysis, it must fulfill some conditions, or any catalyst, not particularly on organocatalysis. It should have a kind of a properties such as it should be stable under moisture and air, it should be inexpensive, easy to handle, and many things. So how this can be achieved? By converting the homogeneous one into the heterogeneous ones. So that I will discuss in my later slides. So if you see, there are basically two type of organocatalysts which are work in two different ways, such as a covalent organocatalysis, where there will be a direct bond between between a catalyst and a substrate. The examples for this include the proline catalyzed reactions, as well as Macmillan's catalyst and the N-heterocyclic carbenes. The other type is a non-covalent organocatalysis, where there is a no direct bond, but there will be a kind of van der Waals forces, and there will be a bonding through a space. The type of catalysts are a Jacobson's catalyst, which have a kind of a thiourea derivatives, and the List's catalyst, which is a Benjamin List catalyst, which is a phosphoric acid. And we have a kind of a catalyst which is a Jorgensen-Hayashi type catalyst, which fall under this category. Basically, the activation modes for a chiral induction in such type of catalysis, they varies from each different type of species. For instance, using a proline catalyzed reactions, it called as enamine catalysis, it proceeds via homoactivation. So this first time the proline was used in the reaction by Hakos and Parrish in 1971. Then it was continued by Benjamin List, Lerner, and Barbas, and there was some Indian scientists also, Kumaraswamy, who also pioneered in this field. However, it was surprising to some of the pioneers did not get awarded for their work. Then there are the Jacobson catalyst, which is proceed via hydrogen bonding catalyst in presence of this thiourea species via a LUMO activation. Recently awarded a Nobel Prize laureate, which is called imidazolidine catalyst, which works in LUMO activation as well as SOMO activation, depending upon the nature of the reaction. In case of radical catalyzed reactions, it proceeds via the singly occupied molecular orbital activation. And the last one is a counter ion directed catalyst, where also it proceeds via a LUMO activation, which developed by Jacobson. So with this introduction, we'll just quickly compare two types of catalyst, which is a homogeneous as well as heterogeneous one. They have their own advantages. In case of homogeneous one, high diffusion, one can get high diffusion as well as greater selectivity, and fine tuning for enantiomeric excess will be a little bit easy. However, they are quite a bit expensive, and there are several separation problems. One cannot reuse them after a reaction. In case of heterogeneous catalysts, they can be recovered, reused, and purification is easy. They are leading to give environmentally friendly processes. They are air as well as moisture stable sometimes. However, there are disadvantages such as fine tuning of particular reaction as well as a mass diffusion problem. So if you see the industrial processes, all processes are categorized into two categories. One is a catalytic process and other one is non-catalytic process. Out of the catalytic process, there are 80% are heterogeneous one, as well as 17% are homogeneous and 3% are biocatalyzed reactions. A typical example of a heterogeneous system is a Haber-Bosch ammonia synthesis, where they use iron oxide nanoparticles for the synthesis of ammonia, as well as the Ziegler-Natta polymerization, where it uses titanium. So why we need to support the organocatalyst? Because there are two main reasons. One is they are difficult to recover and they are expensive in nature, and other one is few are very unstable. So if you see the prices of this catalyst, they are not feasible and they are not feasible to use for everyone's purpose. So that's why if once we make them a heterogeneized version of them, so we can use them for multiple times. So how supported organocatalysts work? So let's take an example of a tea bag. Let's say inside the tea bag we have our catalyst, and this is the reactants. So we need to place this catalyst into the solution, and then it will perform the reaction. At the end of the reaction, you just simply need to pull up your tea bag, and you will have the reaction mixture, which will contain your product. So what can be done with this tea bag now? So this can be treated with acids or some solvents, which will regain its activity, and again it can be used for the performing the next reaction. So they can be regenerated by simple washing with acid source such as HCl or a nitric acid or a simple solvent. So by this means they can be used for infinity times, and it can lead to a highly sustainable process. So once we make the supported catalyst, so next thing is to combine it with the continuous flow process to enhance its process intensification, and the overall reaction will become from non-ideal to ideal chemical process. So what is an ideal chemical process? Statement given by John Cornforth, he says the ideal chemical process is one which is a one arm operator can perform by pouring the reactant into a bathtub and collecting the pure product from the drain hole. So this was his idea, was in 1975. So now it may turn into the real picture in nowadays. So for a demonstration, I have shown here one of the packed bed reactor, and it's filled with the polymer supported catalyst. So with this, I will discuss now which type of catalyst we have developed. So I basically developed two type of catalyst. One was a polystyrene supported trip, which is basically called a chiral phosphoric acid. Other one is polystyrene supported Jorgensen Hayashi type of catalyst. In case of trip catalyst, we have shown the application in enantioselective pictet spindler cyclization, which will be very interesting. I will discuss it in next slides. And other one is a application of this supported Jorgensen Hayashi catalyst in enantioselective Michael addition reaction. So let's start with the first one, which is a polymer supported trip. So this is a typical synthesis of a polymer supported phosphoric acid catalyst, started with the well-known reactions, protection, then followed by bromination, Kumada coupling, some deprotection step, bromination. Then we have a Suzuki reaction to get the monomer, and which gets phosphorylized to get the phosphoric acid. And at the end, one can do the copolymerization in presence of easily available substrate to get this type of polymer supported trip, which is highly air and moisture stable. It can be stored for many years and can be used. This can be characterized by different techniques, not so many, because once they are not soluble in solvent. So we need to use a solid state NMR for a phosphorus compound, as well as the elemental analysis can be performed for getting to know the percentage of phosphorus, and one can calculate what is the actual loading of the catalyst in 1 gram of a polymer supported resin. So after synthesizing the trip, our idea was where we can utilize this trip catalyst. So one of the proposal which was proposed in my proposal, where we wanted to synthesize the tetrahydrobetacarbolines by using a Pictet-Spengler reaction. So why particularly this tetrahydrobetacarbolines? Because if you see, there are several molecules which are present in naturally as well as artificial derivatives. For instance, you can if you see the structure of NITD 609, which is the anti-malarial agent and which is in under clinical trial in Novartis. So in next few years, one can see the replacement for artemisinin kind of drugs with this newly developed drug. So also there are other molecules which has a similar skeleton and had the spiro compounds in their core, which also shows a potent antimalarial activity. Other compounds which involves this type of tetrahydrobetacarbolines, which is the tabertingine, which is derived from this tetralactam, and other drugs they use a phearmilin, which is anti-cancer in nature. And the last one is the tadalafil, which is a commercially available drug, which is acting as an antihypertensive drug. So this gives us inspiration to synthesize such kind of triptolines, or we call it tetrahydrobetacarbolines, in an enantio specific way. Keeping this in mind, we started our reaction optimization on a model reaction where we use the tryptamine and isatine as a model substrate to get this kind of spiro compounds. So we use this polymer supported heterogeneous catalyst for performing the reaction. And we added the temperature as well as solvent, and then we observed the outcome. So we see we got 89% maximum enantiomeric excess in all cases, and at 45 degrees Celsius. However, this can be simply increased by a single crystallization from DCM up to more than 99%. So if you compare this reaction with a homogeneous version, in homogeneous catalyst, it needs more than 24 hours, as well as they are non-recoverable. But in case of these systems, I use a single catalyst for all the optimization. After each reaction, the catalyst was just simply washed with the acidic solution in ethyl acetate. So the generality of the reaction was shown in a broad substrate scope, where we can see the electron neutral as well as donating as well as withdrawing molecules work well to give moderate to excellent yield, as well as good to very good enantiomeric excess.
Recording in progress.
Sorry, there was some disturbance, I think.
No problem, sir. You can continue.
Oh, sorry. I thought my phone is not working out. Oh, it's okay. So yeah, then we went further ahead to see the outcome with the protected isotines, and it also worked well to give a very good to excellent yield as well as an enantiomeric excess. So the key factor is for all the substrate scope, we use a same sample of polymer supported trip. Again, after each reaction, catalyst was just taken and washed with 1 molar HCl in ethyl acetate and other solvents to get all the substrate scope done. So the obsolete configuration was determined by using a single crystal XRD, where we can see it turned out to be the R isomer. So we perform the generality in terms of varying the tryptamine, and then we change the tryptamine part, and we see the bromo substituted as well as fluoro substituted compounds also works well, as well as electron donating compound also work well, and they gave a moderate to good enantiomeric excess and moderate yield. Then we can see the scope and synthetic applications of this reaction for a different type of applications. For instance, we have taken this diketoester to get this tetrahydrobetacarboline in 80% yield with 64% EE. Other one was a cascade reaction where a pictet Spengler followed by a lactamization sequence has been performed, where we got 59% EE with 83% yield. And then this is a precursor for a tabertingene, which is a iboga type alkaloid, which is present in some plants. So then we were interested to see the alpha substituent in tryptamine and how it affects the distereo as well as enantiomer selectivity of the reaction. By placing one CH3 group, it turned out to be the reaction become a non-enantiomer selective, but it was a highly distereo selective. It did not give any enantiomeric excess, and which is possible due to the presence of Thorpe-Ingold effect. In another case, when we use the ester moiety as well instead of methyl, so we got some kind of enantiomeric excess, but the yield was pretty low. And the other enantiomer where the EE was very poor, the yield was good. So this proves that the alpha substituents on the moiety it was not helping for the reaction. So another aspect was to perform the reaction with a piperonal, where we have taken this tryptophan, racemic tryptophan, and reacted with the piperonal under our optimized condition. And we can see we got these precursors for tadalafil with a low enantiomeric excess, but this turned out to be the proof of concept for the reactions, because previously such type of reactions were performed by using a dye substituent at this position. So first time with this kind of catalytic system, we perform this reaction, and this is a proof of concept. So after a few steps, one can achieve this synthesis of tadalafil by using this precursor. So we were happy with the results in batch. So we thought, okay, so let's convert this into the continuous flow and see the outcomes and compare them with the batch reactions. So this is a typical continuous flow setup where we can see these are the pumps used to flow the reactants. Then we have check pole here, which avoids the backflow of the reaction mixture. And here you can see this is a packed bed reactor, and this is our trip catalyst here. This showing the temperature. And then we have a back pressure regulator here. And finally, we get the reaction mixture and our product here. So with this, we again need to optimize this a bit using a continuous flow process because if you remember, in batch conditions, it took 45 degrees Celsius to undergo a reaction smoothly. However, in flow, it was not the condition like that. So we need to change the condition and increase the temperature to 80 degrees Celsius. And we also studied the concentration. This reaction was highly concentration dependent. Not only this, but I would say most of the Pictet-Spengler reactions are concentration dependent. And although when we increase the temperature to a little bit higher, like 100 degrees Celsius, the enantiomeric excess was dropped. And then we went with the optimized condition, which gave us 83% of yield, enantiomeric excess, and 87% of yield. So this enantiomeric excess can be enhanced by a simple recrystallization from DCM, or I would call a precipitation from DCM. And finally, it gave more than 99% EE. With this optimized condition in hand, so one thing I need to mention, let's say in batch, it was taking more than 24 hours, but in a continuous flow operation, we were able to get the first product out from the reaction from 24 minutes. This one was the dramatic change from a time perspective. So we performed the long time experiment to check the stability of catalyst and continuously pumped this reactants for 15 hours. At the end, the outcome was we able to get 11.6 turnover number, and the turnover frequency was 0.7483 millimole of product per millimole of resin per hour. which has a residence time of 24 minutes. And finally, we were able to get 265 milligram product with 83% enantiomeric excess. However, this turns out to be not a good catalyst for long-term perspective, because it was getting deactivated after a certain time. So in that case, what need to be done using we thought to use a cumulative approach where after a certain time, let's say after after flowing 8 ml of solvent, we were just washing it with a 1 molar HCl ethyl acetate and with other solvents, and then again we were loading our reactants in a continuous manner. So you can see up to 10 runs, 10 cycles, it gives a constant enantiomeric excess as well as yield for this reaction. The final outcome was a cumulative turn number was a 43 in this case. So and then we perform the generality in continuous flow, where we perform the simple substrate as well as substitute N protected ones as well as halogenated compound. And the more interesting one was the presence making of this precursor, which is a precursor for natural product. So with this, now I will move to my second topic, which is a polymer supported Jorgensen IASSD catalyzed inertial selective alkyl reactions and their further applications. So we synthesize a library of supported Jorgensen IASSD catalysts. So why we chosen this catalyst? Because if you see, they have a wide variety of application in various transformations. And why proline? Because it's a small molecule and it has a versatile tunable functional group. Presence of a sterically controlled group, such as incorporation of protecting group of OTBS or OTMS, which can lead to the steric bulk and which will help to enhance the enantiomeric excess. And then why 4-hydroxy proline? Because this hydroxy group present at fourth position, which can be anchored with a polymer support, and it will give a heterogeneity for overall reaction. So with this, we synthesize first the polymer supported Jorgensen IASSD catalyst, starting with a simple 4-hydroxyproline with simple reaction steps, and then we perform the Grignard reactions to get this kind of species, and we got finally the monomer. And at the end step, this monomer was polymerized into the gel-like polymer supported compound, which was characterized by using a 13C NMR as well as elemental analysis. So this is the final outcome, which shows the catalyst like this. And after adding this DCM or chloroform into this catalyst, it will swell to give this kind of catalyst. So this is packed into the one of the packed bed reactor, and which has been used for a continuous flow operation. So after making the catalyst, the next step was for which transformation we can use. So we have chosen the asymmetric Michael addition reaction, because if we see the chiral precursor of this reaction, which is quite versatile and can be transformed into this varieties of compounds, such as 3,4-disubstituted piperidines, as well as delta lactones, as well as indoloquinolizidines. So that's why we have chosen this transformation. And with this, then we started, I think this is the other approach, where we have performed the immobilization or polymerization by using a commercially available resin. And we got this with this kind of catalyst. So with this, we started our optimization first in batch, and then we found that basically here there are two catalysts. One is a kind of a Hayashi catalyst, and one is a kind of a Jorgensen one. So, sorry, I make it reverse. This is a Jorgensen one, and this is the Hayashi one. And so the basic difference between them is incorporation of the withdrawing groups over it. So what we observed, let's say if we incorporate the electron withdrawing groups on the catalyst, it was not working with a simple additive such as acetic acid or TFA. which need a specifically calcium triplet to undergo the reaction. However, without electron withdrawing groups, this reaction worked with a simple additive such as acetic acid or moderately with a TFA. So this shows that both of the induction of this catalyst was typically based on the additive. Without additive, the reaction was sluggish and it was not giving a good yield. So with this, getting the best optimized condition, we went for the generality and perform the reaction with the different substrates to get a moderate to good yield as well as moderate to good enantiomeric excess. With this, then we wanted to see the advantage of this catalyst in a continuous flow setup, where we have taken the catalyst, packed into the packed bed, and then flow this two reagents at 60 degrees Celsius, and at the end we are getting the reaction mixture. So basically, we have tried to tune up the flow rate as well as additive. When catalyst 8K, which is substituted, CF3 substituted 1, which not gave a good results, and in presence of acetic acid as well as calcium triplet, initially it not reacted well. However, then next we turn our attention towards this type of catalyst, which was worked good in presence of acetic acid as an additive and the same as a solvent. The main problem was use of calcium triplet in presence of substituted catalyst was not feasible because calcium triplet was not soluble in DCM, and in neat reaction conditions there was a leaching of calcium triplet. So this turned out to be this catalyst was not good for this transformation. And then later we performed the reaction in neat manner, where we have just taken the excess, a little excess of dimethyl malonate, and we got 98% E with 68% yield with the residence time of 50 minutes. So we have taken this as a best condition, where we have used 50 microliter per minute flow rate. So with this, then first we wanted to see the multigram scale reaction in absence of any solvent. So for this reason, we have taken acetic acid, dimethyl malonate, and cinnamaldehyde in one vial, and then it was just passed through the packed bed of the reactor, and then we continuously collected the product. So after the end of the transformation, the outcome was very promising, where we got 97% of enantiomeric excess, and with the turnover frequency of 3.88 millimole, and we got a 5.25 gram product in 4 hours. Sorry. And then the residence time for this reaction was only 55 minutes. After every reaction, the catalyst can be simply washed and can be used for next reaction without any problem. So this gave us a precursor which can be transformed into the phenoxetine, which is one kind of anti-stress drug. And other transformation was taking the 4-fluorocinnamaldehyde and perform the similar type of reaction to get 98% EE with the turnover frequency of 1.3 gram per hour. And if you compare this reaction, as well as if you see the potential of this catalyst, 1 gram of catalyst can give 24 gram of product in 24 hours. So if you see the 10 gram of catalyst, and then it may give a 240 gram of product in 24 hours. For instance, if someone want to use and get this large scale reaction, one has to use more than 2-3 grams of this homogeneous organization IAC catalyst, which will be very expensive in terms of practical aspects. So at the end, one can perform the flow experiment and can use it as a micropilot plant to get the sustainable scale up of the process. So later the generality was shown for this transformation in continuous flow, where the each substrate was run on the continuous stream, where we can see this continuously run it for 4.5 like 4.5 hours, which gives the 18.39 millimole of product. And similarly, not only this type of species, electron donating species as well as electron donating withdrawing species also worked. In case of electron withdrawing, it not worked very well, but it gives us a kind of a moderate yield. So with this, now we thought to where we can use this type of aldol Michael adduct. So for this, we thought to use it for synthesizing complex indoloquinosidines. If we see the retrosynthesis of these molecules, which can be broken into here and which will give a simple two synthons, which can be reacted in presence of acid. And this type of molecules, they are present naturally in reserpine as well as daily supplements such as yohimbine, histidine, and this dihydrocornine menthol. So with this, we started the reaction optimization, where we have taken tryptamine and this aldehyde in one vial, and other vial we taken the trifluoroacetic acid. This reaction does not need any catalyst or something. It needs the equivalent psychometric amount of trifluoroacetic acid. We have used here a simple coiled reactor to perform the reaction. This is this typical setup look where we have taken these series pumps to flow the liquids, and this is the coiled reactor where the reaction was performed, and we got the outcome here. So interestingly, we can see here there was a possibility of epimerization, and this one was the intermediate via Victor-Spengler cyclization. The next step was to get the lactamization at this position, and which was distereoselective in our case. So with this, we got a best condition where we have used 100 microliter flow rate per minute and 2.5 equivalent of trifluoroacetic acid. So with this, then we moved for the substrate scope using a flow in a small scale, and we got pretty promising result. We got a moderate to good yield as well as excellent enantiomeric excess. So this case, if you compare it with a batch, which needs 20 hours of operation, however, in continuous flow, one can perform the reaction at using only 50 minutes of residence time. So the main problem was with this Victor-Spengler cyclizations was the scalability, and they need to be operated at very low concentration, such as 10 millimolar concentration. So for that reason, we thought how we can scale up this reaction. So the well-known approach for using a continuous flow process, which is a numbering up strategy, where instead of one reactor, we can use a multiple reactors. Such as in this case, I have used 3 reactors with a different volume size, and we know then we can gradually increase the flow rate also. Let's say in this case, on the small scale, I have used a 50 microliter. So here I have used a 4 times size of the reactor of previous, so I can use directly 0.2 ml flow rate. So with this, we able to scale up this process, and then we have used a 2 5 ml reactor and 1 10 ml reactor, which gives the 4-fold increase in the outcome of this reaction. So the substrate scope was performed, and which was quite general to give moderate to good yield, and enantiomeric excess was preserved in these reactions because we were using an pure substrate from initial. Then the last application, which was the synthesis of our delta lactones, where we have taken the Michael adduct, and first it was reacted with sodium cyanoborohydride in this coil reactor to give this kind of intermediate after reduction, and this same intermediate was reacted in presence of amberlease which is a kind of polymer supported sulfonic acid, and straight away it gives a reductive cyclization to give this type of delta lactones. This type of lactones has never been synthesized in continuous flow, and which shows the novelty of this transformation. If you compare this transformation to batch, one need to use a 0°C temperature, and it needs 3 days of reaction time to get this kind of delta lactones. However, using a flow process, we just simply can perform the reaction at room temperature, and the time of the reaction was dramatically reduced to only 20 minutes. This is the typical setup when we have performed the reaction under inert atmosphere, where because sodium cyanoborohydride was quite moisture sensitive, and we maintain all the inertness here. So this is the coiled reactor where first the reduction is happening, and this is the packed bed reactor where the cyclization is happening. So with this, now I will conclude my topic, and I will summarize my talk, where we have synthesized a highly robust and air stable catalyst, which was used for a rapid and sustainable flow processes. For the first time, we have demonstrated enhanced selective spectral Spengler cyclization in continuous flow using polymer supported trip catalyst. We have synthesized a complex precursor of iboga type alkaloid as well as tadalafil, and importantly, we have synthesized anti-malarial spiro compounds. Few of them are in under clinical trial with the Novartis company based in Switzerland. Also, we synthesize the various precursors using a solvent-free on a multigram scale for the paroxetine as well as phenoxetine and complex indolophenolazidines as well as the delta lactones. So I would like to acknowledge the organizing team of IASSD for giving me opportunity. My supervisor, postdoc supervisor, Professor Perikas, and financial and research support from Marie Curie and European Commission. So thank you for your kind attention. If you have any questions, I'm very happy to answer that.
Sir, there is a big applaud of claps for you.
Thank you. Thank you so much.
Dear participants, now the session is open for discussion. If you have any question, you may please ask the questions. You can unmute yourself and ask the questions. Sir, we'll wait for a minute if there is any student who wants to ask the question. We'll wait for a minute.
Sure.
Students, you can directly unmute yourself and ask the question if you want.
Dr. Moreshwar,
Yes, sir. Please tell me.
can you guide on that postdoctoral fellowship of Marie Curie? As most of the students are PG students, they will get benefit from your guidance.
Okay. Basically, the fellowship is meant for PhD scholars. So after finishing the PhD, one can avail this kind of fellowships, and the very primary thing need to find the host in European institutions, and after finding the host, so one can draft a proposal, and there are a series of things which need to be taken care, and then there will be a research proposal as well as administrative things, which all must comprises with the 10-page limit. So if we talk more about that, it's like it will be a different session, because it's a quite large topic to discuss. So in short, I can say if one want to apply for such kind of post, one first need to find suitable host, And the information of host or advertisement can be found on European Commission website, or you can simply type Euraccess in the Google tab, and one can find many posts related to that. And there are fellowships by a Marie Curie or a European Commission for master students also who want to pursue their PhD in European institutions. So all such kind of information can be available on Euraccess website, and one need to go through that, and they can put their subject as well as let's say which country they want, under which call they want to enroll themselves, and they can get a nice idea on that website. I hope this helps your question.
Yes, yes. Thank you very much.
Thank you.
Any more questions?
Vishnu sir,
Madam, I think there is no question.
okay, okay, yes, this is just I was asking you. If there are no questions, then I can propose vote of thanks to him. Okay.
Yes,
And-
thank you, ma'am. I now request Chairperson Professor Dr. Bhalla, ma'am, to add comments on the session.
Yes, thank you, ma'am. Dear participants, Dr. Moreshwar Chaudhary, he has explained that his topic of talk was polymer supported organocatalyst for asymmetric continuous flow process, and he has explained the session lecture on batch and continuous flow process. Basically, he has explained in detail the flow chemistry, and how the he also explained how he developed two types of the catalyst and how the evolution of the chemical reactors took place. So he has completely his lecture was very informative, knowledgeable, and insightful. Definitely, I am sure that all the benefited from his, and definitely it will help them in their research process also. Thank you very much, sir, for accepting our invitation, and you have delivered a very nice lecture. Thank you very much,
so
sir.
much.
Thank you.